Faraday's law of induction. Faraday's law of induction. Two systematic situations. If we put a closed conducting loop in a magnetic field and then send a current through the loop, forces due to the magnetic field create a torque to turn the loop. Current loop plus magnetic field, which produced a torque. We have a reverse question. If in the magnetic field we apply a torque to the loop, will it produce current? The answer is yes. That's Faraday's law of induction. It's from United Kingdom. Two experiments. First experiment. We have a loop on the left, connect with a meter. And then we hold a magnetic field put into the loop.
These wire coils and this bar magnet will be used to show electromagnetic induction. The three coils are wired in series to this galvanometer so that current in any one coil will deflect the meter. Here is a single bar magnet pushed slowly into a 10-turn coil, south end first. Here is the same action with a faster push. Here is the magnet being pushed into a 20-turn coil. Here is the magnet moving into the 40-turn coil. Here is the magnet turned around, moving north end first, into the 40-turn coil.
One, a current appears only if there is relative motion between the loop and the magnet. One must move relative to the other. The current disappears when the relative motion between them ceases. 2. Faster motion produces a greater current. 3. If moving the magnetic north pole towards the loop causes, say, clockwise current, then moving the north pole away causes counterclockwise current. And moving the south pole to or away from the loop also causes current, but in the reversed direction. The current produced in the loop is called an induced current. The work done per unit charge in producing that current in moving the conducting electron constituting the current is called the induced electromotive force. And the process of producing the current and electromotive force is called induction. Second experiment. We have two loops. On the left is the same as the first one. Two loops are both addressed, and this loop is connected to an electrical circuit with resistance and battery.
We'll use this wire and a large horseshoe magnet to demonstrate generation of currents from motion in a magnetic field. The wire is hooked to this galvanometer to measure the currents produced. When the wire is moved in the field of the magnet, the meter deflects. As soon as the motion stops, the meter goes back to zero, showing that the current has disappeared. Pulling the wire back out of the magnetic field produces a current in the opposite direction. If we turn the magnet over and repeat the same motions, the directions of the currents are reversed.
Switch on the right loop. The meter suddenly and briefly registers a current, an induced current in the left loop. Switch off the current in the right loop, and another sudden and a brief induced current appears, but in opposite direction. 3. An induced current appears only when the current in the right loop is changing.
These two coils are not connected electrically, but we can use a current in one to induce a current in the other. When this switch is pressed, a current flows in the first coil as seen on this ammeter. Any current flowing in the second coil will be shown on this galvanometer. When the switch is pressed and released rapidly, a current is seen in the second coil. If the switch is now pressed and held down, the current in the second coil pulses rapidly, then drops to zero, even though current is still flowing in the first coil. If the switch is released, what will happen to the current in the second coil? The current pulses rapidly in the opposite direction. If we remove the iron core running between the two coils and repeat the demonstration, the current in the second coil drops dramatically.
Faraday's law of induction. Faraday realized that an electromotive force and a current can be induced in a loop, as in our two experiments, by changing the amount of magnetic field passing through the loop. He further realized that the amount of magnetic field can be visualized in terms of the magnetic field lines passing through the loop. Faraday's law of induction, stated in terms of our experiments, is an electromotive force is induced in the left-hand loop in Figure 1 and 2 when the numbers of magnetic field lines that are passing through the loop is changing. Most important, the actual number of the field lines passing through the loop does not matter. The values of induced electromotive force and induced current are determined by the rate at which that number changes. A quantitative treatment. We define the number of magnetic field lines that they pass through the surface's area by the magnetic flux phi b. We define phi b equal integration b dot dA. We know the integration actually is a sigma, right? Yeah. So we dot this one equal, where dA is a vector of magnitude dA, that is perpendicular to a differential area dA. You have two directions for a perpendicular dA that you can define by yourself. And the integration is to be carried out over the entire surface. This integration. The metric system unit for magnetic flux is Tesla square meter, which is called the Weber, abbreviated WB. 1 Weber to 1 Tesla square meter. Here are the general means by which we can change the magnitude flux through a coil, because it's defined phi b equals integration b dot dA. B dot dA is b dA cosine theta. Theta is the angle between b and dA. So first look at a b. Changing the magnitude b of the magnetic field within the coil. Then the blue one, dA. Change the area of the coil or the portion of that area that happens to lie within the magnetic field. For example, by expanding the coil or sliding it out of the field. 3. Change the angle between the direction of the magnetic field B and the area of coil. For example, by rotating the coil so that E is first perpendicular to the plane of the coil and then is along the plane. Faraday's law of induction. Epsilon equals minus d phi dp. This is the induced electromotive force. This is the change of magnetic field. So this means change magnetic field can change electric field. The magnitude of electromotive force induced in a conducting loop is equal to the rate at which the magnetic field flux Fb so that lobe changes with time. For a closed packed coil of n turns, we just measure one turn. Now you have n turns. We just multiply n in front of this. This is a volt, Weber per second.
This wire coil can generate an electric current using the Earth's magnetic field. Turning the coil in this direction generates a small current, which we can see on a galvanometer. If we move the coil sideways without rotating it, no current is produced. The magnetic flux through the coil changes as the coil is rotated, producing a current. The flux stays constant as the coil is moved to the side and no current is produced.
These two coils of wire are suspended from pendulum arms. The coils are electrically connected through these steel rails so that any current flowing in one coil must also flow through the other. When one of the coils is swung in the magnetic field of a large horseshoe magnet, the other coil also begins to swing between the arms of its own magnet. If one of the magnets is turned around, the second coil swings in the opposite direction as the first coil. If a thick wire is connected between the steel rails, shorting out the current, the effect stops. When a wire coil swings between the poles of a magnet, a voltage is generated in the coil. We'll use this coil connected to a small light bulb to show how that voltage changes as the speed of the moving coil is increased. If we swing the coil into the magnet slowly, the light bulb does not react. A slightly faster swing produces only a dim light. A faster swing lights the bulb brightly. This wire coil surrounds a long iron core. We'll run an alternating current through the coil and watch the effect on metal rings placed over the iron core. This copper ring rises up above the coil and floats at a constant height. A lighter aluminum ring flies completely off the core. If we use this aluminum ring with a small gap, it doesn't move at all. If we cool the solid aluminum ring in liquid nitrogen and repeat the demonstration, it flies even higher than before.
Sample. The long solenoid S shown in cross section in the figure is 200 turns per centimeter and carries a current I 1.5 ampere. Its diameter D is 3.2 centimeter. At its center, we place a 130 turn closed packed coil C of diameter D 2.1 centimeter. The current in the solenoid is reduced to zero at a standing rate of 25 milliseconds. What is the magnitude of electromotive force that is produced in coil C while the current in the solenoids is changing? Now, the current in the solenoid changing is in 25 milliseconds. It changes from maximum to zero. My question, in 25 milliseconds, we have induced electromotive force. Then this M is the turn of this coil where we want to find the E. Okay, so now this is the B in the magnetic field produced by the solenoid. It's mu0 I0 N, we learned before. This is the area of the small coil called pi r squared, or pi d squared over 4. We'll put number inside. This is a constant, this is 1.5, no, this is N. N is defined by turns per unit length. Here the length should be meter, and the given data is per centimeter. So we have to multiply by 100 because 1 meter equal to 100 centimeter. Then we get the answer. N is delta phi of delta t. Delta t is 25 milliseconds. Delta phi is from top to zero, this one. 75 millivolt.